collision. Okay? Cloud-like collisions means that the differential rotation produces shear, and the shear promotes cloud-like collision, and they derive an expression for the relation between the star formation rate surface density and the gas surface density, linked through, again, the rotation frequency and beta, which is related to the epicyclic frequency. And I actually forgot to draw your attention in the previous slide. If you look at this expression for the epicyclic frequency, this parameter beta is simply the R over circular velocity, the derivative of the circular velocity relative to the galactocentric distance. Okay, so we have so far listed out a bunch of recipes for star formation. There is one more missing, okay? And I'm giving you the full enchilada of how many of these star formation relations have been put together by modelers or by people who have tried to interpret the data, because I want to give you a sense for how much degeneracy then that will lead us on to at a later stage. If star formation is regulated by turbulence, we have yet another recipe. A fixed fraction of the molecular gas is converted into star per free-fall time, and according to Krumholz and McKee, that leads to a direct linear relationship between the density of the star formation rate and the density of the molecular gas, which again, for a constant scale height of the disk, translates into a direct linear relationship between the surface density of the star formation rate and the surface density of the molecular gas. After that, how do you relate to the global gas content of galaxies? Because at that point, Tacconi, Young, and Wang and Blitz wanted to relate what they were finding, this linear relation, to the non-linear relation that Rob Kennicott was finding by including both H1 and H2. And so they added this parameter that you can relate. Once you have a direct relationship between the star formation rate and the molecular gas, you can actually relate it to the total content, the gas content of the galaxy, through the ratio of H1 and H2. So R mol in this formula, in this formulation here, R mol is the ratio of H2 to H1, and R mol is linked to the formation of H2 from H1, or the molecular gas from H1. Okay, and according to the model proposed by Elmegren in various papers, it is actually R mol is dependent on the hydrostatic gas pressure in the midplane, pH, and they also give a formula for that. Wang and Blitz derive a value for alpha. Alpha is the exponent that relates R mol to the hydrostatic midplane gas pressure. Wang and Blitz derive 0.8. The prediction from the model, so Elmegren, is between 1.2 and 1.7. But given how little we know about this actual relation, I would say that is sufficiently good. Yes, please.
I missed midplane. Are we still talking? We are talking about clouds, right?
Yeah. So right now, what we are talking actually is the projection of those clouds on the. Practically, you take your galaxy, you take your molecular disk, you put it face on, and you try to calculate the midplane, so in middle. This is a very simplified, of course, it's a very simplified idea, but that's why also the disagreement between the observed alpha and the predicted alpha doesn't worry anyone, right? Because it's you have to make a better approximation in order to actually derive a proper alpha. So the first two figures I showed actually wanted to bring home that the data themselves, at least when you look at whole galaxies, cannot discriminate between relatively different models, like, for instance, the formation of stars over a free-fall time that would predict sigma to the 1.5, and you measure roughly 1.4, which is not too far from 1.5, and on the right-hand side you have that the star formation rate density is related to the ratio of the density of the gas divided by the dynamical timescale, and you still get a good fit. So somehow, by looking at whole galaxies, we end up by having a degeneracy between predictions from different models. You can't quite understand what is going on. Okay? So the problem is that averaging out properties over the 10 kiloparsec or 20 kiloparsec scale of a galaxy doesn't lead you to anything, or at least it doesn't help you discriminating models. So you may want to say, okay, can't do that, let's move into galaxies, inside galaxies, and see what happens. Okay, so let's move at the GMC level and see what happens. Now, when you have an explicit dependence on an explicit mediation through the stellar disk, like the one given by the frequency of rotation, then you have already a built-in dependency, for instance, on the galactocentric distance, right? If you have a localized scaling, like the star formation in a free-fall time, you get a more direct relation to the density of the star formation rate and the density of the cloud. Is like one cloud at a time, okay? And it's expressed as the rho to the 1.5 for the free-fall time. For the turbulence regulated star formation, you get a linear relation. And for the cloud-cloud collision, I think this is the relation is a exponent to the second between the star formation rate and the H2. But Nick can correct me if this is wrong, because he was the one who proposed it in 1986. Are you awake, Nick? There are a lot of corrections. This is a very simplified simplified picture. Perhaps because you relate the star formation rate directly to the molecular gas, generally excluding H1, but you also, if you want to convert it to a surface density, you have to make, again, the simplified assumption that either you have a single, a constant molecular disk height, or you can somehow convolve the variation of the molecular disk across the galaxy. So let's now look at data, finally. Zooming into galaxies. Okay, so this is a plot that shows, again on the vertical axis, the surface density of the star formation rate as a function of two separate gas components. The blue points are the surface density in H1, the black points are the surface density in H2. Okay? This is for one galaxy, M51, but it's roughly been found to be true for most galaxies. What you have is that the H1 reaches a saturation point. This was already remarked by previous talks here. What you have is that above the surface density, the H1 presumably condenses onto H2, and therefore you never go above roughly a surface density of 10 to 20 solar masses per parsec square. So at some point, it makes sense when you look at the individual clouds to look just at the H2 component, also because the H1, in addition, doesn't represent the majority view. Okay, so let's look at spatially-resolved studies. Recent advances in many data are now helping us in trying to look at galaxies, not as just one light bucket or one data point onto a plot of another 100 data points, but to actually try to slice and dice the different galaxies. Now, are we yet at the level of looking at individual molecular clouds in other galaxies? Except for the LMC, SMC, and some heroic efforts in M31 and M33, the answer is no. Typically, we cannot resolve individual clouds in external galaxies. What we do usually is to look at some regions that are definitely smaller than the size of the galaxy, that hopefully target regions of important star formation, and work with those. Those regions tend to be in the typical size range of half a kiloparsec to roughly 2 kiloparsecs, which is well above what you would consider a comfort value for isolating individual clouds. Within these limitations, there have been two main approaches. Okay, one has been to identify the picture on the left-hand side is M51 on the right-hand side is another galaxy, NGC-7793, but it's irrelevant for this discussion, which galaxies we are actually looking at. The one on the left, you can clearly see, I guess, that little red apertures have been dropped on regions where you can clearly see star formation. This is a 24-micron image. The one on the right-hand side, the image on the right-hand side, we have placed a grid on top of the galaxy. And we're looking at regions and trying to measure star formation rates and other properties irrespective of where that grid point is. And both have problems, okay? And I'll try to walk you through the problems that each of them, or each of these two approaches has. The one on the left, you are pre-selecting star-forming regions, which means that you are building in biases into your selection that you have no awareness of. Right? You don't know whether you are excluding some important components that should be there, but because you are fixated on your star-forming regions, you can't quite see them. The one on the right-hand side, there is no pre-selection, right? You're just slicing a dice in a galaxy. But what is the intrinsic point with this kind of approach? The region, so for instance, this region, see if I can, okay. This region here, this is a three-color combination of UV, H-alpha, and 24 micron. Okay, so a white spot is a region of strong star formation. Okay, so this beam here, I lost my pointer. Where is it? Okay. Okay, this beam here will contain a nice, strong region of star formation. But let's look at this one because the other that is split in two. Okay, this one. But what about this beam here? Okay, there doesn't seem to be anything. The problem that you're having there is that now you are trying to extract a star formation rate or a surface density of a star formation rate from a region that could have a large component due to an old stellar population. Could have a contribution to the UV optical and could have 24 contribution to the heating of the dust from the relatively oldish stellar population. So you have to be mindful of what time scales you're applying when you want to calibrate your star formation rates. This is a problem because in both cases, the regions we are looking at are much larger than the size of a molecular cloud. So before I proceed, I just wanted to clarify some lingo because this will appear on over. This is a plot by Bigel et al. Showing again, I will show this plot until you are practically bored to death, of the star formation rate density as a function of the gas density in H2. And what I will indicate from now on, the slope drawn, the best fit slope drawn through this plot will be called gamma H2, and the spread of the data points, the root mean square scatter, will be called sigma H2. And so the so-called scaling law star formation will have the form sigma SFR goes as a sigma gas, in this case sigma H2 to the gamma H2. Okay, controlling the time scales. If we do not want to pre-select our regions, but we want to lay a grid, as I said, we have to control the time scales. How do we do that? A, we want to use a star formation rate indicator that allows us to retrieve both the direct and the dust absorbed components. Okay? So what I have here are two galaxies. One is M51 at the top, and the other is NGC-3521. I'm showing the Spitzer 24 micron images. Okay? On the left-hand side are the original Spitzer 24 micron images. The second panels, show the same images after I've used a program like a H2FOT to remove all the H2 regions. So H2FOT is a program that automatically identifies, seeds and grows H2 regions, and then you can ask the program or manipulate it to actually force it to remove the H2 regions. Okay? So you end up with a relatively smooth distribution of emission, which, however, has some mottles here, some little holes. So you can actually smooth over. The program allows you to do that. And then you can take the first image and subtract from it the third image, and you end up with a map of H2 regions. Okay? So the top one is M51, the bottom one is NGC3521. They are both two nearby grand design spirals. M51 is face-on, NGC3521 is edge-on. So the edge-on galaxy is a little more complicated to deal with, but you can see that the H2 regions only map looks pretty clean. And they're both fairly nearby, around 8 or 9 megaparsecs. Okay, so the question that you want to ask is, okay, with this type of processing, what are you actually removing? How much light are you removing from your system? If I call this smooth component diffuse emission or diffuse light, okay, I see that, for instance, I look at the 24 micron, I remove roughly 50%. I also remove roughly 50% in the UV and the H-alpha as well. And we'll see tomorrow why that is the case. Especially the H-alpha could be the most troublesome because our idea of H-alpha is that it's a short time scale tracer, so why are we removing roughly 50% of it? Because that 50% is what is leaking out of my H2 regions. Okay? That smooth component in H-alpha, and we'll go in detail through that tomorrow if I have time. If I have a region in a position X, okay, that has a diffuse smooth H-alpha emission, that is not that is not necessarily the H-alpha emission produced by the region. It could be produced in region Y, located 1 kiloparsec away. So if I want to measure star formation rates, I have to remove the smooth component from region X, because that smooth component belongs to region Y. But I don't know which region Y1, Y2, or Y3 belongs to, so I'm better off removing it and make allowances later for correction for that problem. What is the impact of this diffuse light component? So these are two plots. Okay, I have 4 plots in total here. The top one, so the ones on the left are the ones in which I have made no attempt to remove this diffuse light. The ones on the right, top and bottom, are the ones in which I have removed the diffuse light. Okay? The top plots measure the star formation rate using a combination of UV and 24 micron. The bottom plots measure the star formation rate with a combination of H-alpha and 24 micron. And we're doing that because we want to test different star formation rate indicators and check whether they give us consistent answers once we control the time scales. Okay? It's an issue of being in control of the time scales. If we get the same answers, it means that we have controlled the time scales by which we are measuring, we're using the star formation rate indicators. Okay, if we do not remove the diffuse light, so the smooth component, we get that in a so-called Schmidt-Kenniker plot, so star formation rate surface density in the vertical axis and molecular gas surface density in the horizontal axis, you measure a mean slope of 0.84, sorry, both using the UV and 24 micron and the H-alpha and 24 micron. So both measurements of star formation gives you the same result, which is comforting because it's telling you know what you are doing. It's actually even more comforting that once you remove the underlying light, you actually recover again the same slope, 1.41 and 1.40 in the two cases. Okay? So not surprisingly, the diffuse light subtraction has a major impact on what you measure in terms of the scaling law star formation. In one case, you recover roughly a linear relation. It's actually 0.8. In the other one, you recover a slope of 1.4. Okay. So, we know how to control time scales now. What do we do next? We ask ourselves the following question. I'm still not measuring individual clouds. What does that mean in terms of what I'm going to obtain for those kind of plots? Okay, those plots in which I plot the surface density star formation rate versus the surface density of molecular gas, and I try to measure the slope and the spread. Well, the two plots, the top plots shows for both M51 and GC3521, the two galaxies I was showing earlier, that as you increase the scale on which you are making the measurement, okay, and you measure the slope, you get a decreasing function as you increase the scale. The same is true if you correlate the scatter in your relation with the scale you're measuring. So what it means is that if I take a region of about 250 parsec in my galaxy, okay, and I slice and dice my galaxy in regions 250 parsecs in size, okay, and then I plot the star formation rate, the surface density, and the H2 surface density on a diagram, and I measure the slope and the spread, I get a slope of 1.9 and a spread of 0.6. The root mean square spread is a 0.6 on the same scale. If I take a region of 1 kiloparsec, and I slice and dice my galaxy in beams of 1 kiloparsec each, and I repeat the same experiment, what do I get? I get a slope of slightly less than 1.4 and a spread of slightly less than 0.5. Okay? So I decrease the spread, which probably doesn't surprise anyone, because I'm averaging out over many more clouds, right? By increasing the size of my beam, I'm averaging out over many more clouds. But I'm also flattening down the slope. Is this kind of size dependency to be expected? Okay. The increase of the root mean square is not new. Okay? This was already seen in various other attempts to do similar analysis. I have a slew of references there, Kennick et al., Filker et al., Onoder et al., Momosa et al. All of them have noticed that if you take two different scales, the smaller scale gives you a larger spread. Okay? And different authors have often reported different values in gamma H2. Okay? But without noticing that there could be a systematic trend as a function of sampling size. So, while the root mean square decreasing for increasing sampling size has been noticed, the change in gamma H2 had not been noticed. But maybe it could have been expected, given a few characteristics. So, now we want to understand what is happening, right? We have these regions in which we see a change in both the slope and the root mean square for increasing sample size, and we have to understand what is happening. So let's look at the characteristic of molecular clouds. And we refer to the Milky Way, and with some additions from the LMC, SMC, and the other nearby galaxies, to try to create a coherent picture and put them into a simulation. Okay, so we assume that the clouds are self-gravitating, they obey the Virial theorem, the mass goes like the size to the square, and the size range goes from about 1 parsec to 100 parsecs. This plot that I'm showing is a plot that I lifted from proceedings by Leo Blitz, and shows the distribution of the velocity dispersion. Yay, I got it. Velocity dispersion, sorry, it's after lunch for me too. Velocity dispersion is a function of the radius of the clouds for all the clouds known in the inner Milky Way, the outer Milky Way, M33, and the LMC. So I try to put a coherent picture together. And what you get is that this size goes from about 1 parsec to about 100 parsecs. We also know that just about everywhere in astronomy, mass functions goes as alpha to the minus 2. Right? You have generally many more small things than large things. Small mass clouds, many more small mass clouds than large mass clouds. Many more slow mass clusters than large mass clusters. Everything goes as alpha to the minus 2. Molecular clouds are no exception. There are variations in the inner Milky Way. The measured slope is minus 1.6. In some other galaxies, you have extremes like minus 2.6, minus 2.9. There might be reasons why they are so different, but by and large, a minus 2 roughly describes most of them. So that means that in your half kiloparsec region or 1 kiloparsec region, you are very much likely to have a lot of 1 parsec scale clouds. Okay? You're going to accommodate a very few 100 parsec scale clouds. And because molecular disks are usually fairly thin, of the order 100, 150 parsecs, you're not going to have a lot of clouds aligned along this line of sight. Typically, you have one or two. So you have practically a monodimensional layer of gas clouds, and you have a fairly small region. What do you want to worry about? We said already this word in the past. Stochastic sampling. You are stochastically sampling your galaxy. How does that work? Let's choose a random box in a galaxy, okay? And let's start filling it up with clouds. First of all, we know that typically the covering factor is small, okay? So we choose a covering factor between 0.1 and 1, giving preference to the small covering factors. So you have a function that describes the covering factor, and then you cover that area with clouds. Now, in my simulations, this area is homogeneously covered with clouds, which are randomly sampled from a mass function, but here I ran out of fantasy and decided to draw clouds, so this is as many as you get. Okay? You fill them with clouds, you give a mass function, you give a range in masses, you relate the rate to the size to the mass through one of the Larson laws, but you give it a scatter. Okay? Never produce a simulation that doesn't have scatters everywhere. Practically, you are producing a Monte Carlo simulation. Okay? That's the short word for it. To each cloud at this point, you add the star formation. And in particular, the recipe we choose is to relate directly the molecular mass cloud to the star formation rate with a range of values for the exponent, and we add scatter as well. Okay? Then we project everything onto dimensions. We add the noise to the measurement of sigma H2. Why sigma H2 and not sigma SFR? Because sigma SFR is, in most observations, measured with a much higher certainty, much higher signal to noise than sigma H2. Sigma H2 right now is our limitation. And then you repeat for 10,000 to 20,000 times and see what you get. Before I proceed, let me give you a couple of words about the direct correlation between star formation rate and cloud mass. Does it make sense? Well, roughly yes, in the sense that if you take the compilation of nearby clouds by Heiderman et al., put the density of star formation rate versus the density of H2, you recover a slope of 1.7, you recover a slope of 1.3 if you just plot directly the star formation rate versus the mass cloud. So power law slope translates in a shallower power law slope, but it's still a power law slope. Why? Because in astronomy, with the type of error bars we deal with, everything looks like a power law. And of course, don't draw any conclusion out of this, because the mass range, the star formation rates, and the fact that I had to assume a spherical cloud approximation, so I assume that all the clouds are spherical, means that you shouldn't believe this, if not to the extent that assuming a direct power law proportionality between a star formation rate and a cloud of molecular gas still make physical sense. There is one more caveat that is often underappreciated. This is a work done by Dashika Narayanan and Junot and collaborators in warning people that we don't measure H2 directly, right? And actually, I think Nick already made this point. What we do is to measure a tracer. And how that tracer translates into a mass is far more complicated than many of us appreciate. And in particular, if you have an intrinsic relation between star formation rate and gas density that goes as a power at 1.5, if you use a CO1 to 0, you still recover roughly 1.5. But say, look, if you use HCN, okay, a higher density tracer, you recover roughly a slope of 1. If you're using a CO2 to 1, you tend to recover a slope that is shallower than 1.5, and so on and so forth for higher density tracers. So as you go to higher density tracers, you tend to recover more and more linear correlation. An intuitive understanding of why. That's the intuitive understanding. As you go to higher and higher density tracers, you are reaching a point in which on the axis you have star formation rate, on the horizontal axis you have star formation rate. You ought to recover a one-to-one correlation. Okay? You reach a point in density in which you are actually tracing the star themselves. So for the extremely high density tracers, the gas is tracing the stars themselves. As you go to lower density tracers, you're putting in stuff that is not, in that moment, collapsing into stars. Okay? Okay, so what do we get from the simulations? So these are a bunch of plots that simply show the so-called mechanical plot, star formation rate density as a function of H2, surface density, and these are for different region sizes. This is we impose again a power law correlation with a factor 2 scatter between these two quantities, between the gas cloud mass and the star formation rate. What do we recover as slopes? So look at the top plot. These are the slopes that are recovered as a function of the logarithmic value of the size of the region in parsecs. If you start with beta equal to, at 200 parsecs, you measured a beta of 2.3, and then you start to decrease, and you reach a value of 1 at 5 kiloparsecs. If you start with beta equal 1.5, you measure 1.7, and you decrease. If you start with beta equal 1, you don't change things by a lot, because you're sliding your data points along a one-to-one correlation, so you're not making a lot of mess, okay? So what you get is that the beta equal 1, so the direct relation between the gas cloud and the star formation rate remains a direct correlation, even in this case. Measuring the dispersion, you can see immediately that the dispersion is the highest for the steepest correlation and decreases as you go to flatter and flatter correlations. How does this work if you change the scatter between your mass cloud and your star formation rate? What kind of scatter am I talking about when I'm talking about this kind of scatter? I'm simply saying that if a certain cloud is giving me a certain star formation rate, I add a scatter in logarithmic space that in the previous case was a factor 2. I can produce twice as much star formation rate and half as much. Now I'm making also the experiment that there is a direct one-to-one correlation between the two, which I call the scatter equals 0, and a 4 times scatter. Okay, for each gas cloud, I can produce 4 times more star formation rate and 4 times less. As you can immediately see, there isn't just an impact. If you compare the top and the bottom, you don't see simply an impact on the scatter of the recovered correlation. You actually also affect this recovered slope. Because you are dealing with a stochastic effect, okay? You are stochastically your mass function, and you are spreading it along one of your own stochastically sampled quantity, which is the density of the star formation the density of the gas, okay? So in practice, you have an impact both on the recovered slope and the scatter. In addition, you find a common trend that as you increase the region, what you end up having is a one-to-one correlation. Why? Because when your region is big enough, as I said earlier, you're sampling fully the mass function of clouds, all beams are identical to each other, and therefore at that point they start sliding on a one-to-one correlation. As for fun, I also added and subtracted diffuse stellar and dust components to see what kind of effects, but we can have a very intuitive understanding of what those components do. Let's say I claim, okay, my clouds are forming stars at a rate that is proportional to the mass of the cloud, but then I say that the smallest cloud do not form any stars. What is happening? This is what I call the B equal 1 with a threshold. I remove 33% of the star formation rate at the bottom, 50% and 67%. As you can see, my measure slope increases. Let's say I take a beta equal 1.5 between gas cloud and star formation rate, and I add some flat component. The flat component I strive to remove in N51 and GC3521, I add it on, back into the mix. What do? Depending on how much I add, if I add 30%, the measured slope will be roughly 1, even if I started with an intrinsic slope of 1.5. Okay? So let's compare it with the observations. The faint gray data points are the data. On the left-hand side, you have the measured slope. This is slightly different from what I showed earlier because the previous plot was in linear scale. Here I'm showing the logarithmic scale of the region I'm sampling, okay, in both plots. On the vertical axis is the measured slope. On the left-hand side plot. On the right-hand side plot is the scatter. Okay? Okay. What you can see is that for the scatter, I would say that both the black and red black and red models are, more or less reproduce the data. The blue don't do it very much. What are these three models? The three colors, red, black, and blue, identify the three star formation laws that I tested. I'm a little reluctant to call them star formation laws because they simply correlate the star formation rate to the mass of the gas cloud to some power, okay? The star formation laws that have been worked out in the literature typically correlate the density of these two quantities. But let's call them star formation law for a shorthand. The red case is the beta equal 1.0, so direct correlation, then you have 1.5, and then you have 2.0. These are the three best fitting models that could be found without violating other observational constraints. So in the case of gamma H2, sigma H2, which is the scatter on the data points, two of the models seems to be to give roughly decent results, okay? The 1.5 than 1, while the beta equal 2.0 seems to be off. For the same models applied to recovered slopes, you can see that only the 1.5 produce a decent result. Now, what are those percentage up there? In order to get the beta equal 1.0 as close as possible to a measured slope of almost 2, what I had to do is to steepen it up. 5 more minutes? Okay, good. Is to steepen it up considerably, meaning that I had to remove some of the star formation, because the only way I can steepen up a one-to-one slope is to by removing some of the star formation, add the clouds as empty clouds. Okay? These are clouds that contribute to the horizontal axis but not to the vertical axis. That steepens up my relation. In order to flatten out the 2.0, I had to add some background, some non-molecular bearing contribution to the star formation rate that is actually my diffuse light. So I could flatten it out a little bit. Yet the only one that seems to be fitting is the 1.5 with a 10% threshold. I can play around with the numbers, so maybe make things a little more extreme for the direct correlation between the gas clouds and star formation rate, and remove as much of the underlying star formation rate from the clouds. So the faint clouds get more and more, the star formation rate removed, up to the point that I removed up to 50% and 67%. And actually between those two limits, the magenta and the red lines seem to have at least embraced the data. But look what happens to the sigma. Okay? Sigma becomes too steep and is completely off. So to conclude, since I was given the 5 minutes warning, we are in a position now to actually go inside galaxies and look at the scaling laws of star formation on a region-by-region basis. We're not yet at the on the cloud-by-cloud basis, except for the closest galaxies, but at least we have regions that are between 100 and 1 kiloparsec in size, or a few hundred to a kiloparsec in size. Hopefully, if we zoom into galaxies, we can remove some of the degeneracy that we saw happening between models when we look at galaxies at full data points. Like one galaxy, one data point, we run into degeneracies for discriminating among models of star formation. The reason different authors have obtained different results might be due to the fact that so far stochastic sampling has been built into the predictions for the scaling laws of star formation. And in particular, the observation that the decreasing function, that the slope and the scatter of the scaling law are both decreasing function of the region size, first has not been fully appreciated yet. More measurements will be needed to actually see if it's a general property of all galaxies. But this result can actually be accounted for once you take into account that within your regions, you're actually stochastically sampling the molecular clouds. The moment we'll be able to look at clouds individually, we'll have a much better handling of what is happening. Thank you.
Well, you gave a fantastic review on the subject. And somewhere in the middle of your talk, you opened the Pandora box. That's when you said that this is a textbook material.
You mean,
yeah.
The beginning, only the beginning. The GC stability is
Yeah, that's where I'm heading.
Okay, go ahead.
So here is the question.
Yeah, sure.
In the Schmidt-Kennicott law, there is no specification of what type of gas participates in the stability.
Yes, indeed.
It's a surface density, which is about between 3 to 10 solar masses per square parsec. I must say that things happen locally when stars form. So one needs to come with translation from the surface density to the volume density. I never saw an intelligent translation of this. And when the translation is published, then, one can just estimate the size, length of the Jeans length. And if you talk about 10 to the 4 degrees gas, it's 4 or 5 kiloparsecs. I just don't believe that the gas cares. The star-forming gas cares what happens 5 kiloparsecs away. So that is something, this is not good. So the other possibility is that as the Jeans instability starts, there is a rapid conversion of atomic gas to molecular. That is interesting, but if you really think about this and you don't believe in conspiracies, that most probably the gas was going from atomic to molecular already before the instability. But then this is not a Jeans instability. This is some thermochemical or chemothermal instability. Even more interesting is that numerical simulations, if you translate this 10 solar masses per square parsec into the Jeans lengths, you get a critical density of somewhere between 0.1 to 0.5 per cubic centimeters, particles per cubic centimeters. This is what is used in numerical simulation as a threshold. And this is not a local instability because it takes you in the cube of 5.5 kiloparsecs, which is of the order of the size of a galaxy. So what is your opinion on this?
That you're pointing out at the fact that we don't understand this type of phenomena very well. So this is a very simplified presentation that gives an intuitive understanding for why people are fighting over the 1 versus 1.5 versus 2 slopes, right? If let me say, let me try to cast it in this broader scheme. Over the recent 6 or 7 years, there have been many papers looking at this spatially resolved Schmidt-Kennicut law, right? And different authors have published different slopes, claiming better agreement with one model versus another, right? So what I've done, I've taken these models as presented by these authors, trying to make sense out of them, because different authors have different takes, and put them on a slide. Now, whether that is the only possible way you can understand star formation, it's actually beyond what I wanted to describe. I just wanted to describe the fact that even within these different residues, so even within a very simplified model, you still can get different residues, okay? And even within those limited set of recipes, you don't have a one-to-one easy translation to what you see on the face of the galaxies. Because what you're doing when you're looking at a region that is half a kiloparsec in size, you're not just looking at a single molecular cloud, right? You're looking at a random sampling of molecular clouds. So even within this very simplified scenario, you're still running into troubles. Okay? Then you can actually make things a lot more complicated by adding all these considerations that you're talking about.
I mean, I do agree with what you just said. I mean, it's really crucial, because if you form stars at a density of Kennicut-Schmidt law, which is 0.1 to 0.5, say, particles per cubic centimeter, or you increase artificially this threshold for star formation, the volume threshold, not the, to 3 orders of magnitude, I mean, these two type of models don't have anything to do with each other. You get completely different star formation, completely different galaxies, and so on. I
agree. At that point, the problem moves from trying to explain why you got this type of slopes, to try to explain why you get a different threshold, right? And I haven't touched the threshold because that's another, it's a separate kind of work.
You have an opinion.
I have an opinion which I will not express because otherwise we can stay here until tomorrow morning. Fighting over the threshold issue. The threshold is a very important issue which I haven't touched on purpose, but I agree with you. It's a separate kind of worms, and it's an horrendous problem.
Maybe I can make some comments, because I think you've made the situation more complex than it needs to be. And in the first lecture, what I advocated was, one, H1, nobody has yet, as far as I know, seen a star forming in an H1 cloud. So take total gas content out of the issue. H1 may be important for forming molecular clouds, but it's not important for star formation.
I agree.
So that may well be the origin of the so-called threshold in Rob Kennick's analysis, that below some threshold, approximately 10 to the 21 per square centimeter, you simply don't have very many molecular clouds. And that's the reason why I showed that disks tend to have molecular material above that 10 to the 21 squared centimeter. So then the other thing I advocated was looking at our galaxy. In our galaxy, these studies back in the 80s, they measured 2,000 GMCs. About 500 of those have masses estimated not from CO, but from virial estimation, assuming gravitational equilibrium, which is roughly justified. They also have infrared luminosities from IRES. And I showed a plot which shows roughly constant LIR over M virial as a function of cloud mass. There is scatter, and there is a little bit of increase in that ratio when you get up to the highest mass clouds. So the point that I was trying to make there is that there's no evidence for that much nonlinear dependence of the luminosity of the star formation rate from simply proportional to mass of clouds. And I think looking at our galaxy, it avoids all this issue of smoothing over larger scales in the clouds. It avoids the issue of background subtraction, et cetera. You get roughly linear dependence. Now, let's see, there was another. So the one thing you can't do in our galaxy is to investigate azimuthal dependencies of star formation efficiencies, because there's no very good agreement about where are spiral arms, where are inner arm regions, because you're confusing stuff along the line of sight, and various people argue one or another. A lot of the theoreticians are, for example, Krumholtz and McKee, adopting a model where they say, I can understand star formation if I say 2% of the mass of the cloud forms stars in a free fall time. Well, that's not an understanding of star formation. The 2% is the important factor. It's arbitrarily adopted to match the observations. But since the first days of molecular line astronomy, nobody understands the reason for that 2%, the low efficiency. Why don't these clouds just collapse and form stars? So it's not, in my opinion, a theoretical explanation. You might as well just go to the simple mass dependence of the star formation rate and apply it in other galaxies.
So it's actually a well-taken point that there is a linear correlation. I showed earlier that if you have a highly nonlinear relation between the densities, you still flatten out your relation with the mass. It's a relation. Right. So, exactly. So what you're doing in practice, you start with a highly nonlinear correlation between the star formation rate, density, and the gas density. You end up with a roughly flat correlation between the masses and the star formation rate.
Resolve individual clouds. That's not the explanation for the linearity.
Right. But then you have the problem. I mean, I relate to what you say that the Milky Way offers us 2,000 clouds, but it's one data point. It is not a very active galaxy to start with. So it might be worth going to places that are more active and see how they behave. At that point, you're dealing with all these issues, at least until you start resolving them into individual clouds, you start to run into this issue of how you deal with stochastic sum, how you deal with diffuse light, how you deal with all these other problems. Now, like you, I would rather work with the original cloud and see how they behave in other galaxies. We cannot do that, but we have a lot of data that we can try to get into a shape that can be used for inferring some of these relationships. So I think that it's important to actually look at those relationships and in other galaxies, even if that means that you have to elaborate a little bit. But you also have to understand what kind of assumptions you are making by deciding that you are taking a 1 kiloparsec square region rather than a 200 parsec. Why one versus the other? And what does it mean? And that's where the stochastic sampling comes in.
When you're looking at the effects of stochastic sampling of the molecular cloud mass function, are you still imposing the criterion of constant surface density? And if yes, should you start to be worried about
constant surface density?
Surface density, one of the last one.
The one that the last criteria. So that's one of the reasons why I'm using a direct correlation between star formation rate and cloud mass, because I'm not modeling the surface density. But also, let's remember that if the roughly constant surface density, it doesn't apply in a rigorous term, path is roughly okay because there's a shallow slope. There is a shallow dependence with the cloud mass. Actually, Mark Heyer has a study in 2009 showing that. So it's an excellent point in the sense that we haven't implemented that, but it's a small error. The biggest spread comes from the stochastic sampling itself. More than the stochastic sampling itself, from the fact that you're stochastically sampling along an axis, and then you're using that axis to plot your correlation. Because the mass cloud and the surface density of clouds are related to each other. And so that's where your spread in slopes and scatter in the relation comes from. Because you're using the same axis that you're trying to measure to actually, you're spreading it out. So that's where all the problems come from.
Okay, now time for coffee. Thanks to the speaker again.